Welcome to A-Level and EP Physics. In today's lesson, we will discuss past paper questions from October-November 2023, Paper 4, Variant 1. As always we will discuss these questions in detail so you can improve your conceptual understanding of physics and also you can have better understanding of these exam questions. Let's study together, let's improve together. Question second part A says, define specific heat capacity. So first of all, we need to understand specific heat capacity is a quantity. So you need to define quantity in terms of other quantities. So this is very important point. When you need to define quantity, you need to define quantity in terms of other quantities, and when you need to define a unit, you have to define in terms of other units. Now let's try to define specific heat capacity. So first of all, we can simply say Q is equal to mc delta T. From here you can see if m is the unit mass, so m is unit mass, so we can simply say if m is unit mass and delta T is the unit change in temperature, so this is unit change in temperature. So this is unit change in temperature, means temperature changes by 1 Kelvin or 1 degree Celsius. Then this C, this is the specific heat capacity. So this one is the specific heat capacity. So this specific heat capacity will be equal to the amount of thermal energy needed. So the amount of thermal energy needed to raise temperature of unit mass by unit change in temperature, that amount of thermal energy is specific heat capacity. So we have specific heat capacity. If you look at the beauty of the equation, we have specific heat capacity means if we have unit mass and we change temperature by 1 unit temperature change, how much energy we need? That is the specific heat capacity. Now if the mass is double, so amount of heat means the thermal energy needed, that will be double. And if we keep the mass same and we want double change in temperature, means 2 times, so the thermal energy we need to supply, that has to be 2 times. So this is how these things are linked together. So if you try to understand like this will help you to understand physics in a better way. So your way of thinking will be like a physicist, and physics itself is a way of thinking to explain the nature. Now let me explain you this one in a little bit different way. It's a beautiful concept. Imagine that this one is the unit mass. So I can simply say this is unit mass. We can also understand this one in this way. This is unit mass and we place temperature thermometer inside. So you can simply imagine this one is thermometer. So we place thermometer inside this one. So here we have the bulb of thermometer. So this is our thermometer we place inside this one. And let's say temperature of this on this thermometer is 21 degrees Celsius. And if we change this temperature from 20 to 21 degrees Celsius, so this is 20, if we change to 21, how much thermal energy we have to supply? That thermal energy is the specific heat capacity. So here we have the thermal energy, we can say this is Q. So how much thermal energy we need to supply? That Q will be equal to C. So this is how you need to understand physics, and this is how you can define specific heat capacity. Now let me show you the answer, how you can write down the answer. In your answer you can mention these points, and simply you can say the amount of thermal energy required per unit mass per unit change in temperature. If you write on this, you will get 2 marks. So this is what is specific heat capacity. When the mass is unit mass and we want unit change in temperature, so the amount of thermal energy we need to supply, that is specific heat capacity. Part B says an ideal gas of mass 0.35 kg is heated at a constant pressure of 2.0 times 10 to 5 pascals. So that its internal energy increases by 7,600 joules. During this process, the volume of the gas increases from 0.038 cubic meters to 0.063 cubic meters, and temperature increases by 56 degrees Celsius. Show that the magnitude of the work done on the gas is 5,000 joules. For this question, first thing we need to understand, it is given to us that pressure is constant. During this process, pressure is constant. So simply we can use for this question W is equal to P times delta V. And also you need to understand in this case, as volume is increasing, so it means work is done by gas. So in this case, work is done by gas. So this is very important one you need to understand. You can also simply imagine this one. We have this cylinder, and inside this cylinder we have the gas. So this is our initial volume, then gas expanded to this volume. So this is V final. So gas is expanding, so it means work is done by gas. So work is done by gas. So how we can calculate the magnitude? So we have value of P, that is given to us 2.0 times 10 to 5 pascals, and we have the final volume, that is 0.063 minus we have 0.038 meters cube. Now if we solve this one, we will get our final answer, that is equal to 5000 joules. So this is the final answer, and this is the work done by gas. So in this case, work done by gas is positive, and it's the same as work done on the gas. So the negative, so work done by gas, we can say work done by gas. Work done by gas is positive, so this is negative of work done on gas, negative. If question asks you to calculate work done on gas, simply not the magnitude, so the work done on gas in this case is negative because work is done by gas. So these are some important points you need to understand. Next time they can ask you about these concepts, so try to understand these things. Second part says explain whether the work done on the gas is positive or negative. We have already discussed this point, so let me little bit highlight and then we will answer this question. So here we have the cylinder. So first of all, it was given to us that initial volume is 0.038 and volume of the gas increases to 0.063. So it simply means that the gas is expanding, so the work is done by gas, and work done on gas, in this case work done on gas, this will be negative of work done by gas. So work done on gas is negative because in this case gas is expanding, so work is done by gas. If gas is compressed, so simply you can say from here work done on gas is positive if the gas is compressed. So this is one thing you can remember. And work done on gas is negative if gas expand. So we can say if gas expand, in this case gas is expanding, so work done by gas is, work done on gas is negative, work done by gas is positive. And so this is simply you need to write down. You can simply say work is done by gas as gas is expanding against external pressure, so work done on gas is negative. Third part says determine the magnitude of the thermal energy Q transferred to the gas. This is a typical question about first law of thermodynamics. So simply we can say delta U, this is equal to Q plus W, and W is the work done on gas. So this is work done on gas. Now let me explain you a little bit about this equation. So here we have change in internal energy, and this change in internal energy, this one will be positive if Q is positive. So if Q is positive means the change in internal energy 100% will be positive if Q is positive, if work done on gas is also positive, so the change in internal energy, that will be positive. But if Q is positive, W is negative, then we need to compare which one is bigger. Then we can explain the change in internal energy, it will be positive or negative. Now also let's try to understand when this change will be negative. Change in internal energy, this one will be negative if thermal energy release means Q is negative, means the thermal energy is released, we can simply say delta Q, means the thermal energy is taken away from the system. So delta U will be negative. And if work done on gas is also negative, it means 100% change in internal energy will be negative. But if one is positive, Q is positive, W is negative, it means you need to check which one is bigger. So the change in internal energy will be according to that one. Now for this question, so these are the points you need to understand. This is what's the meaning of this equation. Delta U is positive if thermal energy is added to the system and work is done on the system, means on the gas, on system here is gas, work is done on the gas. So these are few things very useful. Now for this question, it is given to us that internal energy increases by 7600 joules. We need to find out value of Q, but we have already discussed that work done on gas in this case is negative because gas is expanding. So here we have negative. So this one is negative. Now you can simply say, because this change is positive, so Q has to be positive. So Q has to be positive. So simply Q from here you can say this will be equal to 7600 plus 5000 joules. So the final answer is 12,600 joules. So this is how we can answer. So when you do question, try to understand what actually is happening and try to get feelings about that. When you start feeling, it means you started to learn physics, you started to understand physics. So the answer for this question is 12,600. We can also write on this one 12.6 kilojoules, but this is given in joules, so you have to write down 12,600. Question 4 says calculate the specific capacity of the gas for this process. Give a unit with your answer. Value of Q we have just calculated, that is equal to 12,600 joule, mean the amount of thermal energy supplied we have calculated, and rise in temperature, change in temperature is given to us, that is equal to 56 degrees Celsius, and we have the mass of the gas, that is equal to 0.35 kgs. Now we need to calculate value of C. Before we calculate value of C, mean the specific heat capacity, one very important point you need to understand that change in temperature in degrees Celsius is equal to change in temperature in degree Kelvin. So this point is very important. Now we need to calculate C, so we can simply say this is equal to Q divided by M times delta T. So we have value of Q, that is 12,600 divided by 0.35, and here we have this is 56. So we can also say this is the same as 56 Kelvin because the change in temperature 56 degrees Celsius is equal to change in temperature of 56 Kelvin. So from here we will get our answer, that will be equal to 640 joules per kg per Kelvin. So this is better way to write on joules per kg per Kelvin. But you can also use degrees Celsius because change in temperature in degrees Celsius is equal to change in temperature in Kelvins. So you can also write on degrees Celsius, but it's better to write on Kelvin. So our final answer is 640 and the unit is joules per kg per Kelvin. So this is how you need to answer. Part C says the gas in B is now heated at constant volume rather than at constant pressure. The increase in internal energy of the gas is the same as in B. Use the first law of thermodynamics to explain whether the specific heat capacity of the gas for this process is less than, the same as, or greater than the answer in B4. So first of all, we need to understand in this case first law of thermodynamics, delta U is equal to Q plus W. For the second process, volume is constant. So if volume is constant, it means that work done by gas, this one will be equal to 0. So it simply means that in this case, the change in internal energy, this is equal to amount of thermal energy supplied. And change in internal energy we have calculated, that was given to us in the question, and the value was equal to 5600 joules. So new value of Q, we can say the new value of Q, this is equal to 5600 joules. In the last part, in part B, we have calculated old value of Q, that was equal to 12600 joules. So the value of Q new in this case is less than the previous value of Q, or we can say Q old. So from here we can write down, now C is equal to Q over M times delta T, same as same rise in temperature. So if Q decrease, it means that C will decrease. So the value of C will be lower. So this is how we can answer. Because in this question, in the second part, first thing we can understand, for the last part we have already discussed, the volume increases, so there is a work done by gas. So this is the first case, volume increases. But in this part, volume is fixed, so no work is done by gas. As no work is done by gas, so all the thermal energy supplied is used to increase the internal energy of the gas. So less thermal energy is needed. If work is done by gas, more thermal energy is needed. If work is not done by gas, less thermal energy is needed for the same change in temperature and also same change in internal energy. So these are very important points you need to understand like this, not just try to memorize the answer of this question, try to understand what actually is happening, the conceptual understanding. I hope this makes sense to you. Now let me show you how you can write down your answer. In the answer, you can mention these points. You can say same gain in internal energy, so same rise in temperature. No change in volume, so no work is done. As no work is done, so less thermal energy is needed for the same temperature change, hence lower specific heat capacity. So this is how we need to answer. So these 2 points are very important. So here work is. So let's try to understand a little bit in a different way. Let's say this is case 1 and let's say this is case 2, and here we can draw another one. So in this case gas is compressed. So let's say we have here, then we compress this one and the new volume has decreased. So this is kind of exercise for you. Now can you try to answer in which case the amount of thermal energy supplied has to be the greatest for the same rise in temperature, for the same rise in internal energy. If this is same, so which one is greater? So this is second, this is third, so which one is greater? Is Q1 is greater, is Q2 is greater, or Q3 is greater? Q1, here we have Q2 and here we have Q3. So which one is the greatest? Very good exercise. Now first of all, if you look at this case, case 1, the amount of thermal energy supplied has to be greatest in which case? So I hope you say in case 1 it has to be greatest because work done is negative. So we can rewrite here Q plus W, this is equal to delta U. If this one is negative, this has to be positive and its value has to be greater. So it means in this case highest amount of thermal energy needed for the same rise in temperature. So we can say Q1 has to be the greatest. How about the second one? Second one has to be this one. So we can write down the second case. If W is equal to 0, it means delta U is equal to Q. So it means this one has to be the second one. And this is third one because if W is positive, this is also positive. So for the same rise in internal energy, it means Q has to be lower. So in this case Q1 has to be greater than Q2 and Q2 has to be greater than Q3. Very important concept. Try to understand this one. If still it is not clear to you and if you have any questions, please leave your questions in comments. And if these videos are helping you and they are helping you to improve your understanding, please like and subscribe, because your encouragement is very important. If you are looking for detailed notes, well written notes with specifications, and also worksheets with detailed solution, join Patreon. On Patreon, you will find these resources. Question 3 part A says the product PV for an ideal gas is given by this equation. P is the pressure of the gas and V is the volume of the gas. State the meaning of the symbols capital N, small m and mean square speed in this equation. So what N is representing? N is representing number of molecules of the gas, and m is the mass of single molecule, and this is mean square speed of molecules. So very basic question. So simply you need to write down the names, what n is representing, what m is representing, and what mean square speed is representing. This symbol is representing. This symbol is mean square speed. So in your answer, simply you just need to write down number of molecules of the gas, mass of one molecule of the gas, mean square speed of molecules. Second part says use the equation of state for an ideal gas to show that average translational kinetic energy of a molecule of the gas at thermodynamic temperature is given by this equation. So first of all, we have to use equation of state for an ideal gas. So we have to start with PV equal to nRT. In the final equation, we don't need gas constant, so simply we can write down this in different form. PV is equal to N times K times T. So we can use the second form of this. So we can write down PV, this is equal to N times K times T. At the beginning of the question, it is given to us that PV is equal to this. And you can also find this one in the data. In the given equation, this is also given. So simply we can replace PV with 1 by 3 N times M times mean square speed. This is equal to N times K times T. N is common, so we can simply cancel. So here we have M times mean square speed. This will be equal to 3 times KT. This has to be kinetic energy, so we can divide both sides by 2. So this one is kinetic energy of average kinetic energy of a molecule, and this is equal to 3 by 2 K times T. This is what we need to prove. Very common question and also very straightforward one. If you understand, PV is equal to this and PV is equal to NKT. Part B says the surface of a star consists mainly of gas that may be assumed to be ideal. The molecules of the gas have a root mean square speed of 9,300 meters per second. The mass of a molecule of the gas is equal to this. Determine to 3 significant figures the temperature of the surface of the star. Now it is given to us the surface has gas, is mainly made of gas. So simply we need to determine the temperature of gas, and this gas is ideal. We can assume this gas is ideal. So for ideal gas, simply we can say EK, this is equal to 3 by 2 K times T, and EK is the average kinetic energy of each molecule. So we can say this is 1 by 2 M times mean square speed, and this is equal to 3 by 2 K times T. From here we can cancel 1 by 2, so we will get T, this is equal to M times mean square speed divided by 3 times K. Now simply we need to plug in values. We have value of mass, that is 3.34 times 10 to minus 27 kgs. We need to be careful with units, and this is root mean square speed. So it means that if we have the mean square speed, you take root of that is given to you, and that is 9,300 meters per second. Now if we take square of this one, we will get mean square speed, that will be equal to 9,300. So this will be meter square second square per second square. Now simply we can plug in here. So this is square divided by, we have 3 times Boltzmann constant, that is 1.38 times 10 to minus 23. And if we solve this one, we will get 6980 Kelvin. So this is up to 3 SF. So we can say this is 6980 Kelvin and this is up to 3 SF. So you can also write this is 6.98 times 10 to 3 Kelvin. So this is up to 3 SF. Part C says the radiant flux intensity of the radiation from the star in B is 2.52 times 10 to minus 18 watts per square meter. When observed at a distance of 4.16 times 10 to 16 meters from the star, calculate the luminosity of the star, give a unit with your answer. So first of all, for this question, it is given to us. You can simply imagine we have a star here. So this one is the star. And if we look at a distance of, as it is given in the question, so we can move our star to the center. So imagine that star is here. At this point, flux intensity is given to us. So at this point, we have value of F, that is 2.52 times 10 to minus 8 watts per square meter. And the distance we have, this distance is also given to us. Value of T is given to us. And we need to find out what is the luminosity of the star. Means the power of the star, the emitted power of the star. We have to find out. So for that purpose, simply we can say F is equal to the luminosity of the star divided by 4 pi d square. We need to find out L in this case, so we can write down L is equal to F times 4 pi times d square. Now simply we need to plug in these values. We have value of F, that is equal to 2.52 times 10 to minus 8 multiplied by 4 pi times d square, and value of d is 4.16 times 10 to 16 meters, square of this value. Now if we solve, we will get value of L, that is equal to 5.48 times 10 to 26 watts. So this is our final answer. We can write on here 5.48 times 10 to 26 and the unit is watt, because luminosity is the power emitted by the star. So unit of power is watt. Second part says determine the radius of the star. So simply we need to use Stefan-Boltzmann law. And Stefan-Boltzmann law simply tells us that luminosity is equal to Stefan-Boltzmann constant times surface area of the star times T to the power of 4. So we can rewrite this one. So here we have sigma, this is constant, and surface area is 4 pi r square T to the power of 4. We need to find out value of R. We have value of L, that is 5.48 times 10 to 26, and sigma is constant and its value is 5.67 times 10 to minus 8. We have 4 pi and here is r square, and value of T is 6980. We have just calculated. Now if we simply solve for R, we will get the radius of the star, and that is size of the star. So we will get 5.69 times 10 to 8 meters. So this is radius of the star. So this is how you can calculate. Part D says the gas at the surface of a star has a very high pressure. Use the basic assumptions of the kinetic theory to suggest why in practice a gas at the surface of a star is unlikely to behave as an ideal gas. So first of all, we need to understand condition for an ideal gas. So we can write down a gas is an ideal gas. So we can say a gas can behave as an ideal gas if no forces between molecules, negligible forces between molecules. If we write down here, negligible forces between molecules. So we can say negligible forces between molecules. This is condition for an ideal gas. Now, if pressure is greater, it means molecules will be very close to each other, so there will be forces between molecules. So gas will not behave as an ideal gas at high pressure. And when a gas can behave as an ideal gas, if pressure is low and temperature is high temperature, gas can behave as an ideal gas. High temperature means molecules, they have higher kinetic energies, so they are away from each other. So in that case, volume of the molecule is negligible as compared with volume of the gas. So gases behave as an ideal gases at low pressure and high temperature. But if pressure is high, gases do not behave as an ideal gas. So this is the main point. I hope this is clear to you. Now let me show you how to write down the answer. In answer, you can just mention this point. You can say as pressure is very high, molecules are very close to each other, so forces between molecules are not negligible. Because this is condition for an ideal gas. If we treat any gas as an ideal gas, we assume that forces between molecules are negligible, and that is only possible if molecules are away from each other, mean the pressure is low and temperature is high. So these are the things you need to understand for ideal gases and also for this question. I hope this video was helpful. If this video was helpful, please like and subscribe because that is kind of encouragement for your teacher. And also, if you have any questions, please leave your questions in comments and I will try to answer as soon as possible. And if you're looking for well-written notes and worksheets with detailed solution and more resources, you can check Patreon. On Patreon, you will find all these resources. On Patreon, you can find resources for Edexcel, you can find resources for Cambridge A-level physics, IGCSE physics, then also for physics competitions like Physics Bowl, BPHO, and also Oxford University and Cambridge University admission test like PAT and ENGA. All these resources are on Patreon. So if you need them, you can join Patreon. I'll try to upload the remaining questions as soon as possible. See you in next video.